In January 2026, the U.S. government made a significant policy adjustment. After years of tightening export bans, they authorized the sale of advanced AI chips, specifically NVIDIA's H200 processors, to approved commercial buyers in China. But when the trade path was finally cleared, the demand had vanished. Behind the scenes, Chinese authorities instructed their domestic tech giants and cloud providers to pass on the imported hardware, effectively excluding American suppliers from the market they once dominated. This refusal marked a sharp departure from decades of trade logic. It indicated that the assumption of an integrated global supply chain, where the U.S. designed and China consumed, was beginning to collapse. To understand this shift, look back at 1974. The Nixon administration lifted Cold War export restrictions on high-grade computers, treating technology as a tool for diplomatic engagement. That decision helped establish a period of deep reliance on Western engineering that supported China's industrial growth for 40 years. Moving from that era of integration to today's rejection involves a complex cycle. It is a history defined by Western containment efforts, early state-directed industrial failures, and recent rapid technical adaptations. In March 1986, 4 prominent defense scientists sent a confidential letter to Deng Xiaoping. They warned that if China failed to master high technology, it faced a future of economic and military marginalization. This led to the 863 program, a state-funded R&D initiative targeting microelectronics. By the 1990s, the focus shifted to hardware manufacturing through Project 908, a massive attempt to build a domestic microelectronics fabrication plant. The project struggled. Extreme bureaucratic delays and slow financing meant that by the time the production lines were finally operational in the mid-1990s, the factory's technology was already generations behind the global state-of-the-art. Its successor, Project 909, achieved commercial viability only by forming a joint venture with Japan's NEC. While the plant produced wafers, it remained dependent on foreign operational blueprints and intellectual property. These early efforts demonstrated that state capital alone couldn't guarantee hardware independence, as long as the underlying designs and tools were sourced from abroad. The dynamic changed in October 2022. The U.S. Commerce Department introduced strict performance thresholds to counter China's Made in China 2025 strategy, which sought to fuse commercial technology with military modernization. The new rules blocked the sale of top-tier GPUs used for AI training, along with the extreme ultraviolet lithography machines needed to make them. For the first time, U.S. policy moved from routine competition toward targeted technological denial. When chipmakers tried to export modified, lower-performance versions to comply with the law, the U.S. closed those loopholes in April 2025. This move forced companies like NVIDIA to absorb billions in canceled orders and stopped the flow of workaround hardware. This strategy left Chinese AI developers without a reliable external source for high-end processors, forcing them to find alternative ways to support their computing needs. One of those alternatives emerged from a startup called DeepSeek. Its founder, Liang Wenfeng, had anticipated the restrictions and stockpiled thousands of older NVIDIA chips before the bans took full effect. DeepSeek couldn't rely on the Western approach of scaling up through massive hardware clusters. Instead, they focused on maximizing mathematical and algorithmic efficiency to get frontier-level performance out of their limited, older hardware. They utilized a mixture of experts architecture. Rather than using the entire model to process every task, the system only activates a small fraction of its parameters for any individual token, which significantly reduces the computational load. Combined with techniques that compressed the model's memory requirements, DeepSeek drastically reduced the compute power needed for complex reasoning. These breakthroughs allowed a Chinese firm to train a high-performing AI model for a fraction of Western costs. By optimizing software, they diminished the immediate impact of the hardware embargo. On the hardware side, domestic manufacturers like SMIC began bypassing the ban on advanced tools. By using older, deep ultraviolet machines in a multi-step layering process, they successfully produced 7-nanometer AI chips within China. At the same time, state mandates are driving research into non-silicon alternatives, such as carbon nanotube processors, to bypass the limitations of conventional lithography entirely. Hardware denial did not halt production. Instead, it accelerated the deployment of domestic capital and forced the development of an independent manufacturing pipeline. This brings us back to the 2026 plot twist. China rejected the newly allowed U.S. chips because the preceding years of restrictions had forced domestic firms to standardize their workloads on local hardware and architectural workarounds. We are now seeing the emergence of two separate technological stacks. The Western stack is characterized by capital-intensive compute clusters, advanced lithography, and proprietary instruction sets. The Chinese stack is defining itself through necessity, prioritizing algorithmic efficiency, open-source architectures, and domestic fabrication methods. Washington's attempt to slow Chinese AI progress instead accelerated a bifurcation of the global technology sector into two distinct ecosystems, each operating under its own strategic and technical priorities.